Hey everyone, welcome back. I'm Kelly from Signature Solar, and today we're diving into AC and DC coupled solar battery systems. What are they, how do they work, and which one might be the right fit for your solar setup? We'll explore both in detail, including different configurations, real-world examples, and their advantages and disadvantages. Let's jump right in. Let's start by going over some basic concepts about solar power, electricity, and the components that make up a solar energy system. Understanding these fundamentals will make it easier to grasp how different solar setups work and which might be the best fit for your needs. Solar panels generate electricity through a process called the photovoltaic effect. This electricity is in the form of direct current, which we call DC for short. In DC power, the current flows in one direction, which is ideal for charging batteries. However, most homes and the electrical grid use alternating current, also called AC, where the current changes direction periodically. To use the electricity from solar panels in your home or send it to the grid, we need to convert DC to AC. This conversion is where an inverter comes into play. An inverter is a crucial component in solar energy systems because it converts the DC power produced by the solar panels into AC power, making it usable for home appliances and capable of being fed back into the grid. Now, you might hear a lot of different terms like solar inverter, MPPT, charge controller, and battery inverter. It can get a little confusing. Let's break these down. Solar inverter. This is simply an inverter that is specifically designed for solar energy systems, with its primary function being to convert DC power from solar panels into AC power. More generally, an inverter can also convert AC to DC depending on the system's needs. Essentially, it transforms power from one form to another. MPPTs and charge controller. While an inverter converts DC to AC or vice versa, a charge controller doesn't convert power at all, although it is also known as a battery inverter. It can be either a standalone component or contained within the inverter. It only works in DC-coupled systems and controls how much power flows from the solar panels to the batteries, as well as from the inverter to the batteries. Most inverters contain MPPTs, which aid in maximum power production from your panels by utilizing maximum power point tracking. The MPPTs is where your PV will connect inside your inverter. They act to ensure the solar panels operate at their maximum efficiency. When used together, their role is to optimize the charging of batteries by ensuring they receive the maximum possible power from the solar panels without overcharging your batteries. In short, the inverter is the device that changes the type of current, DC to AC or AC to DC, while the MPPT and charge controller manage the flow of electricity in a DC-coupled system to keep the batteries charged efficiently. Now, let's talk about microinverters and optimizers, two components often used in solar systems to maximize the performance of individual solar panels. Microinverters. A microinverter is a small inverter attached to each solar panel. Unlike a central inverter that handles the output of an entire array of panels, microinverters convert DC to AC right at each panel. This means every panel operates independently. So, if one panel is shaded or not performing well, it doesn't affect the performance of the others. A significant advantage of microinverters is the redundancy they offer. If a part of the system fails, such as one microinverter or panel, the rest of the system continues to work. This setup allows you to replace the faulty component at your convenience without losing power to the entire system. Optimizers. Optimizers also work at the panel level, but unlike microinverters, they don't convert DC to AC. Instead, they maximize the DC power output of each panel before sending it to a central inverter. This central inverter then converts the combined DC power from all the panels into AC power. While optimizers can enhance the overall efficiency of a solar system, they have a key drawback compared to microinverters. If a single optimizer or central string inverter fails, the entire system can go offline, leaving you without power until the issue is identified and repaired. This lack of redundancy can be a significant disadvantage, especially if the system fails during a critical time. Microinverters are typically used in an AC-coupled system because they output AC power directly from each panel. This AC power can then be used immediately in the home, sent to the grid, or in some systems used to charge batteries after being converted back to DC by a separate battery inverter. The independent operation of microinverters provides greater reliability and flexibility, ensuring that your system continues to generate power even if one component fails. Optimizers are generally used in DC-coupled systems. In AC-coupled setups, they work with a central inverter to convert DC to AC. In DC-coupled systems, they enhance the efficiency of solar panels and work with an MPPT or charge controller to manage power flow to the batteries. However, their reliance on a central inverter means the entire system can be affected if any single point fails. By understanding the role of inverters, MPPTs, microinverters, and optimizers, you can better appreciate how AC and DC coupled systems are structured and function to provide power for your home or business. Now that we've got the basics down, let's talk about AC coupled and DC coupled solar battery systems. Whether a system is AC or DC coupled depends on how the inverter is connected and what role it plays in converting and storing power. In an AC coupled system, the DC power produced by the solar panels is first converted to AC using an interactive inverter before it connects to the batteries. Since batteries store power as DC, the AC power must be converted back to DC to charge the batteries. Similarly, when the batteries discharge, the DC power is converted back to AC for use in your home or to be sent to the grid. This process requires an additional multi-mode inverter, leading to energy losses from the multiple conversions, making it less efficient overall. However, AC-coupled systems can be more versatile and easier to add onto existing solar setups. In a DC-coupled system, the process is more efficient because the power from the solar panels can go directly to the batteries without being converted. A single inverter manages the conversion, and the DC power charges the batteries directly. The power is only converted to AC when it's needed for use in your home or for sending to the grid. This setup minimizes energy losses and makes DC-coupled systems generally more efficient. Let's dive deeper into each type of system. In this diagram, you see a DC-coupled system. The solar panels generate DC power, which flows directly to the batteries through a charge controller. Now, sometimes our charge controllers exist as their own module, but in our newer all-in-one inverters, they can also be contained within the inverter itself as part of the built-in MPPT. Since the batteries store power in DC, there's no need for conversion at this stage, making this the most efficient way to charge a battery. The DC power is only converted to AC when needed for home use or when sending back to the grid. This simplicity means fewer losses in energy conversion, which means higher efficiency overall. There are obviously some advantages and disadvantages of each type of system. Let's discuss some of the pros and cons of the DC-coupled systems. Some of the pros are higher efficiency. One of the biggest advantages of a DC-coupled system is its efficiency. Because the energy from the solar panels flows directly into the batteries without needing to convert to AC first, you avoid the energy losses associated with multiple conversions. The direct DC to DC transfer means more of the power your panels generate ends up stored in your batteries, making it an ideal choice for maximizing energy retention, especially in off-grid setups. Integrated design. DC-coupled systems often come as a package from a single manufacturer. This integrated approach means that the inverter, batteries, and charge controller are designed to work together seamlessly. Compatibility issues are minimized, making installation more straightforward. Since all components are engineered to communicate effectively, you get a more streamlined setup that can reduce troubleshooting and improve the overall performance of the system. Ideal for off-grid use. If you're considering an off-grid solar system, DC coupling is a great option. In off-grid scenarios, it's often advantageous to use DC appliances directly, such as DC lighting or DC-powered refrigerators. This direct use of DC power eliminates the need for an inverter to convert DC to AC for every load, thereby reducing energy losses. You can have a small inverter dedicated only to essential AC loads, while most of your appliances run efficiently on DC power, maximizing the use of your solar-generated energy. Simpler electrical upgrades. With a DC-coupled system, you're generally dealing with a single inverter, which simplifies the electrical calculations needed for installation. For instance, the National Electric Code requires specific calculations when integrating solar and battery systems into a home's electrical panel. Since a DC-coupled system uses one inverter, these calculations are more straightforward, often resulting in fewer modifications to your electrical system and, in many cases, lower installation costs. Flexibility in sizing. DC-coupled systems allow some flexibility in designing your solar array. For instance, you can sometimes oversize your solar array relative to your inverter. In this configuration, excess solar energy can be directed to the batteries even when the inverter is at maximum output. This means you can install a larger solar array to maximize energy generation and ensure your batteries are charged without being limited strictly by the inverter's capacity. Now, some of the cons are inverter limitation. A key drawback of DC-coupled systems is their reliance on a single inverter's capacity. The inverter acts as the bottleneck for how much power can be used at any given moment. For example, if you have a 10 kilowatt solar array and a 10 kilowatt inverter, the maximum power that you can supply to your home or the grid at any time is 10 kilowatts, regardless of whether your battery bank could discharge more. This limitation can restrict the total power available, particularly during peak usage periods. Potential weakest link. In a DC-coupled system, the weakest component determines the system's overall performance. If your inverter has a lower capacity than your battery bank, the inverter will throttle the power output to its own limit. For example, even if you have a battery bank capable of discharging at 15 kilowatts, but your inverter is only rated for 10 kilowatts, you will be limited to that 10 kilowatt output. This constraint means careful planning is required to ensure that your system components are well matched to avoid underutilizing your solar panels or battery storage. Less flexibility for retrofit. If you're looking to add a battery system to an existing grid-tied solar setup, a DC-coupled system might not be the easiest option. Many existing solar installations are designed with AC coupling in mind, and integrating a DC-coupled system often requires replacing or significantly modifying the existing inverter setup. This lack of flexibility can result in higher cost and complexity for homeowners wanting to upgrade their current solar systems with battery storage. Compatibility requirements. Since DC-coupled systems often come as an integrated package, they require careful planning to ensure all components, panels, inverters, batteries are compatible. This compatibility is less flexible compared to AC-coupled systems, where components from different manufacturers can often work together. Therefore, selecting a DC-coupled system may limit your options to specific brands and models that are designed to be used together. Now, let's look at an AC-coupled system. Here, the solar panels produce DC power, which is first converted to AC by a solar inverter for use in the home or export to the grid. When the system includes batteries, the AC power is converted back to DC by a battery inverter to charge the batteries. This process allows flexibility in system design, but results in some efficiency losses due to the double conversion. Now, let's go through the benefits and downsides of AC-coupled systems. Some of the pros are retrofitting ease. One of the standout benefits of AC-coupled systems is their flexibility when retrofitting to an existing solar setup. If you already have a grid-tied solar system in place and want to add batteries later, an AC-coupled system allows you to do this without replacing your existing solar inverter. The AC-coupled battery inverter can be installed on the AC side of your system, seamlessly integrating with your current setup. This flexibility makes AC-coupled systems ideal for homeowners who want to enhance their solar systems with energy storage without starting from scratch. Additive power. AC-coupled systems can combine the output of both the solar inverter and the battery inverter. This means if you have a 10 kilowatt solar inverter and a 5 kilowatt battery inverter, you can potentially supply 15 kilowatts of power to your home or grid simultaneously. This additive effect can be particularly useful during peak times when you need more power than what your solar array can generate alone. It also provides a performance boost when the sun is shining, allowing you to take full advantage of both solar generation and battery storage. Versatility. AC-coupled systems are incredibly versatile. They can be designed to work with different brands of solar and battery inverters, offering a mix and match approach. This versatility allows homeowners to select the best components from various manufacturers without being locked into a single brand's ecosystem. Additionally, modern AC-coupled systems can be used for both on-grid and off-grid applications, giving you flexibility to scale and adapt your solar system to meet changing energy needs. Backup power capabilities. Many AC-coupled systems are designed with backup power capabilities in mind. In the event of a grid outage, the battery inverter can create a microgrid that powers your essential loads. Some advanced AC-coupled systems even allow the solar inverter to continue operating during an outage, so your solar panels can charge your batteries and power your home even when the grid is down. This ability to maintain power during outages can be a crucial advantage, especially in areas prone to power interruptions. Supports larger systems. AC-coupled systems are well suited for larger solar installations. They can easily be scaled by adding additional solar inverters and battery inverters, providing greater power output and energy storage capacity. This scalability makes them ideal for complex, high-demand applications, such as homes with high energy consumption or commercial properties looking for extensive solar and battery setups. Redundancy. An important advantage of AC-coupled systems is the built-in redundancy. If one part of the system fails, such as the solar inverter or the battery inverter, the other parts can often continue to function independently. For instance, if the solar inverter goes down, the battery inverter can still provide power from this stored energy. Similarly, if the battery inverter has an issue, the solar inverter can still generate power for your home or the grid. This redundancy ensures that you have multiple pathways to keep your home powered, enhancing the overall reliability of the system. Now, some of the cons are efficiency loss. The primary disadvantage of the AC-coupled systems is the efficiency loss due to multiple conversions. In an AC-coupled setup, solar energy is converted from DC to AC by the solar inverter for home use or grid export. Then, if the energy is to be stored in batteries, it needs to be converted back to DC by the battery inverter and later back to AC when the stored energy is used. Each conversion results in energy losses, typically around 5 to 10% per conversion, making AC-coupled systems less efficient overall compared to DC-coupled systems. Complex electrical upgrades. AC-coupled systems can be more complex to integrate into your home's electrical system. Because of the power output of the solar inverter and the battery inverter is additive, the total system capacity must be carefully calculated. This can make the electrical upgrades more complicated and potentially more expensive. For instance, you may need to upgrade your main electrical panel or wiring to handle the combined output of both inverters, which can add to the overall installation cost and complexity. Dependence on communication. In an AC-coupled system, the battery inverter often relies on communication with a smart energy meter or energy management system to monitor the energy flow between the grid, solar panels, and battery. If this communication link fails or is not set up correctly, the system may not operate optimally. For example, the battery may not charge efficiently or provide backup power correctly. Ensuring reliable communication between components is essential for the proper functioning of an AC-coupled system. Grid dependency for solar inverter. In some AC coupled configurations, the solar inverter depends on the grid being present to operate. This means that if the grid goes down, the solar panels may not be able to generate power, even if you have a battery inverter in place. While some advanced AC coupled systems can operate a grid down scenario, they often require a more complex setup to ensure that the solar inverter can continue functioning during a power outage. This added complexity can increase the installation cost and require more advanced equipment. Limited by inverter capacity in backup mode. While AC coupled systems can provide backup power during outages, they're often limited by the capacity of the battery inverter. For instance, if you have a 5 kilowatt battery inverter, your backup power capacity during an outage is capped at that 5 kilowatts, regardless of how much solar generation is available. This limitation means that during a power outage, you might not be able to power all of your home's electrical loads, especially if they exceed the capacity of the battery inverter. Understanding these detailed pros and cons helps in evaluating whether an AC coupled system is the right fit for your needs, whether you're looking for redundancy, retrofitting options, or a scalable solar solution. As we've explored both AC and DC coupled systems, it's important to compare their efficiency. DC coupled systems are generally more efficient when it comes to storing energy in batteries, as the power flows directly from the solar panels to the batteries without requiring multiple conversions. This makes DC coupling ideal for nighttime or low light conditions where stored energy becomes essential. On the other hand, AC coupled systems can be very efficient for daytime power use, especially when paired with microinverters. Microinverters often have high conversion efficiencies ranging from 97 to 99%, making them excellent for high-light conditions. For instance, running high-energy loads like HVAC systems during hot summer days can be handled efficiently with an AC-coupled setup where the power is used immediately rather than stored. To summarize, DC-coupled systems excel in low light or nighttime efficiency, making them optimal for energy storage. AC-coupled systems shine in daytime efficiency for direct use of solar power. In some advanced setups, you might find both AC and DC coupling combined for greater reliability and flexibility. For example, an off-grid system might use a DC-coupled configuration to ensure direct battery charging for efficiency. At the same time, an AC-coupled inverter allows scaling up the system to include additional solar panels or provide power when the grid is down. In this setup, you get the best of both worlds, high efficiency and flexibility in power management. One practical example is using an in-phase microinverter system in conjunction with an inverter like the EG4 18K. This approach allows you to leverage the strengths of both AC and DC coupling, providing a robust and versatile solar power system. The in-phase system uses microinverters, which are installed on each solar panel. These microinverters convert the DC power generated by the panels directly into AC power at the panel level. This AC power can then be used into your home or sent back to the grid. The EG4 18K inverter allows you to integrate this AC-coupled solar power into your energy storage system. Here's how it works. Connection through the generator port. The in-phase system's AC output can be connected directly to the EG4 18K via its generator or gen terminal as part of an AC coupling setup. This connection allows the inverter to manage the AC power generated by the in-phase microinverters, using it to charge the batteries, supply power to your home, or send power back to the grid. Simultaneous AC and DC solar inputs. The EG4 18K inverter can accept both PV solar inputs to its 3 MPPTs or maximum power point tracking channels and AC-coupled solar input from the in-phase system simultaneously. The AC-coupled solar input can handle up to 90 amps of AC power or 21.6 kilowatts of solar. This means that you can have a substantial amount of solar power coming from your existing AC-coupled system, maximizing solar power output. In addition to the AC-coupled input, the EG4 18K's MPPT channels can manage up to 18 kilowatts of solar power. Of this, 12 kilowatts of continuous power can be used for powering your loads, charging your battery, or backfeeding the utility grid. Combined with the AC coupled input, up to 33.6 kilowatts of AC power could potentially be sent back to the grid. For this level of backfeed, a feeder tap or supply side tap will be required as this point of utility interconnection to safely and efficiently manage the power flow to the grid. Powerful backup capabilities. With this setup, you can harness a significant amount of solar power while also having the flexibility to store energy for use during grid outages. The in-phase microinverters continue to generate power when the grid is up, allowing the EG4 18K to use this AC power effectively. During a power outage, the hybrid inverter acts as a power source, allowing the grid interactive inverter to synchronize and supply power to the in-phase system. Now, let's take it a step further by incorporating DC-coupled solar into the same system. The EG4 18K inverter has the capability to operate as both an AC and DC-coupled system simultaneously. Integrated DC-coupled system. The 3 MPPT channels on the EG4 18K can be directly connected to DC solar panels. This DC power can go straight into the inverter to charge the batteries without conversion losses, maintaining high efficiency, 99.9% based on their spec sheet. The direct DC charging allows you to optimize solar energy storage, ensuring your batteries are charged efficiently and quickly. Enhance flexibility and redundancy. By integrating both AC and DC solar inputs, you have multiple pathways to harness and store solar energy. If one part of the system fails, such as the AC-coupled microinverters, you still have the DC-coupled solar panels working to charge the batteries and supply power. This redundancy provides a more resilient power system that can handle various scenarios, including grid outages and equipment failures. Balancing power sources. With this hybrid approach, the inverter can intelligently manage power sources. For instance, during the day, the system can use the DC-coupled solar panels to charge the batteries efficiently while the AC-coupled in-phase system provides power to the home or backfeeds the grid. If the batteries are full or if there's excess solar production, the system can direct this energy to the grid, ensuring optimal use of all available power. The result, a comprehensive high-capacity solar system by integrating the in-phase microinverter or other microinverters such as NEP, Aptos, or others with the EG4 18K PV. You can create a comprehensive solar power solution that leverages both AC and DC coupling. This setup allows for massive solar generation. Up to 33.6 kilowatts of AC power can be sent back to the grid, maximizing the solar generation capacity of your installation. Efficient energy storage. Direct DC charging of batteries ensures that solar energy is stored with minimal losses, enhancing the overall efficiency of the system. Robust backup power. In the event of a power outage, the system can seamlessly switch to battery power, providing reliable backup for your essential loads. Scalability and redundancy. The ability to combine both AC and DC coupled solar inputs gives you the flexibility to expand your system and the redundancy to ensure continuous power supply even if one part of the system encounters an issue. This real-world example showcases how integrating both AC and DC coupled systems can result in a highly versatile and powerful solar energy solution, offering the benefits of both efficiency and flexibility while providing a reliable backup power source. Do you already have a DC-coupled system with an 18K? The most cost-effective way to boost your system's output up to 33.6 kilowatts may be by integrating an AC-coupled microinverter system. Already have an AC-coupled microinverter system? EG4's 18K with its powerful AC coupling capabilities through that generator port is hard to beat. The great thing about AC coupling and DC coupling is that their benefits often complement each other. Whether you're looking to expand your system or create a more reliable power setup, both configurations can work together in many combinations to maximize efficiency, storage, and output. By blending the strengths of both, you get a versatile and robust solar power solution tailored to your unique needs. So, should you go with an AC coupled or DC coupled system? If efficiency and simplicity are your priorities, especially in an off-grid scenario, a DC coupled system may be the way to go. If you're retrofitting an existing solar setup with batteries or need more flexibility in scaling your system, an AC coupled system might suit you better. Remember, it's about matching the system to your specific needs and conditions. Consider factors like your home's electrical setup, your budget, whether you're on-grid or off-grid, and future expansion plans. Ultimately, choosing the right system involves weighing the pros and cons based on your individual needs. In conclusion, both AC and DC coupled systems have unique strengths and serve different needs. Understanding how each works, as well as their advantages and their disadvantages, will help you choose the best setup for your home or business. As always, work with reputable manufacturers and, if needed, certified installers to ensure your system meets your energy goals. Thanks for joining me today. I hope this breakdown helped you understand the differences between AC coupled and DC coupled systems. If you have any questions or need further guidance, feel free to reach out to us at Signature Solar. For more products, installations, tips, tricks, and insights into your solar journey, don't forget to subscribe so you'll get all the latest information. I'm Kelly with Signature Solar, where we believe that solar is for everyone. We'll see you next time.